Bingo. Located 250 feet, so we have L. L equals 250 feet. Okay. From the power source supplied with 10 AWG copper, right? So 10 AWG. Right, is this going to be useful for our calculation? Not quite, not yet, right? So what do we need to do with it?
Circular mode.
So if we say number 10 AWG is equal to
10,380.
excellent. So the motor has a full load current drop of 24 amps. This tells us that I equals 24 amps. Okay. And so at this point we have length, we have current, we have two that we're using for single phase, that we have our circular mills, right? And so the K is going to depend whether this is copper or aluminum. What do we see? Bingo. K is equal to, anybody remember? 12.9. Excellent, very good. 12.9. Right. And so in this case, remember, we cover up the quantity that we're solving for. Right. So we get that our voltage drop is equal to 2KIL over Cm. The nice thing is that we have all these values, right? So direct substitution, 2 times 12.9 times 24 times 250 over 10,380. All right. So everybody have the latest iPhone 17 Pro Max when I calculate this one? All right, cool. So we'll take a second to do it. I'm going to do it, but over here. 2, 24, 250. All right, I have an answer. What does everybody else have? 10,380. Oh, good. Yeah, I have the exact same thing. That's where I got the. Yeah. So 14.93. 3. Good stuff. I'll take 9133. I'll take 913. 14.913. What? 14.913. What we look at? We've done some more calculations. Yeah.
So we forgot to draw.
Exactly. 14.913. So that means that at the other end, please note that for motors produced slows, the total current of the one in question is at 100% out. Okay, I don't know if it'll ask this on the next one, but if we heard that there should not be more than a 5% drop, actually this is for motors, so it doesn't count. But as an exercise, how is this and 5% compared to your supply? All right, never mind. But keep in mind that if you could, I guess, divide by 0.05, you can compare it to see if it does meet your 5% requirement according to the NEC. But this is a motor feeder. Generally, those are going to be about 8%, not 5% in this case. All right, there you go. So for those of you that wanted to double check your work, this is exactly what we did over here. So prepare in your assignment this week that you may just have a bunch of different numbers. You may be asked to solve a different quantity, that kind of thing. But if you can do one, you can do them all, right? So just manipulate your equation accordingly. Any questions on that? Yeah, so nothing super out of the ordinary, right? So let's go to voltage drop example 2. Suppose you have a 3-phase. Okay, so let's redo this here. Now we have a 3-phase. Ooh, complicated. It's going to be 3 times as difficult, right? So suppose you have a 3-phase. What does that tell us right off the bat?
1.372.
Excellent. Yep. 18 ampere load rated 480 volts with 390 feet of conductor. What size aluminum conductor? Ooh, it's not copper, it's aluminum, right? Will prevent the voltage drop from exceeding 3%. So the way they ask this is obviously a little more convoluted, but nothing's going to get past this here. So let's start with what we know. 3-phase current is equal to 18 amps. 480 volts. I'll write that at the top. 390 feet. What size aluminum conductor? Okay, then what does that tell us about our K value?
It's 21.9, I think.
Trust but verify, another useful expression. Excellent. Well done. All right. Prevent the voltage drop from exceeding 3%. So what exactly does this 3% mean? Where does it come into play in terms of this question?
3% of the original 480 volts.
Excellent. Yep. And so this will be kind of a reference towards the end of final check. So 480 volts times 3%, right? And mathematically, it's I think 480 times 0.03, right? So anybody, well, historical, that percent, like in Spanish, por ciento, for every 100 means divided by 100. So 3% just means 3 over 100. If you were to plug that in your calculator, you get 0.3. So percent for every 100 out of 100. Right? That's where that comes from. So that hopefully can help you easily kind of navigate between percent, decimal, even fractions, right? Because we're going to need to be able to be very comfortable with those. So once you plug this in your calculator, 480 times 0.03, right? 14.4 volts. This means that this is your maximum allowable voltage drop. Does that make sense? Cool. So that's really taking the previous question, a final step to say, hey, calculate the voltage drop, but also make sure that in this particular installation, it checks out according to, say, NEC requirements or whatever it may be. Cool. So let's go ahead and calculate, what else do we know about this guy here?
CM.
What size aluminum conductor? Interesting. So this is saying, what is the circular mode, right? So you're exactly right. That's what we're looking to find. So let's go ahead and write out our equation. Again, cover up the value you're looking for so that you can see how they interact here. So your circular mills is going to be equal to 1.732 L over the voltage drop, which actually calculated right there. So that's going to be 1.732 times 21.2 times 18 times 90 14.4. Take a second to do that one. So we have 1.3732 times 1.2 times 18 390 divided by 14.4. Okay, cool. I got a number. What do you guys have?
994 and a half.
17,994. Okay, did you actually take square root of 3?
Oh, no, I did not.
Okay, no, that's fine, that's fine. I'm just saying that might be a part of the discrepancy, if ever, right? But yeah, I have 17,900.22. And again, it might depend if you actually use a square root function on your 3 or how many digits you carry on this guy.
I used 1.722 and I got 18,490.
It's a 390.
So I got the same number, 17,900.22.
Okay. Yeah, feel free to try that again. Either way, I think we're pretty much in the ballpark of,
1.732.
yeah. And the good news is we're not too far off because what are we going to do with this number? Even if it's a few decimal places off, even if you didn't carry one of the digits on the root 3 factor. Remember, what is it that we're doing with this number? The question states, what size conductor? So, that being said, let's look at our Chapter 9, Table 8 excerpt here that says you'll be able to convert your circular mills, which is what we have here. I always encourage writing units because like by the end of it, you're like, wait, what did I calculate again? Just like we remembered volts. In this case, we remembered circular mills. So which of these is going to be the suitable application? What size would you go with? Sean?
6 gauge conductor?
6 gauge, 6 AWG. But number 8's cheaper, right? And we want to cut corners. So depending on your customer, unfortunately the customer is always right, but definitely Sean is exactly right. NEC is the minimum installation recommendation for the protection of personnel and property. Absolutely, I would agree with you that even though it is over-spec, let's say, our number 6 AWG, which is good for 26,240, is going to be our size of choice. Excellent, well done. Anybody not clear on why we chose one of the other? I think my ridiculous example hit home. Okay, correct. So, there we go. Yep. So about 17,900. But either way, with your number, you were off by, I mean, give or take a few circular mills. We would have ended up sizing up to the exact same amount. So, referring to the wire size chart, we would select 6 AWG. All right, very good. And if you followed along thus far, and again, feel free to stumble with the equation and rework it to your needs during the assignment this week, and you'll be just fine. So troubleshooting hints for wires and connectors. For many types of electronic equipment, an open circuit may be caused by wire conductors, connectors, or switch contacts. Wires and printed wiring can be checked for continuity with an ohm meter. And we've kind of done that to an extent, and we're definitely going to do some more, especially when we get to our medium voltage or high voltage application. We're going to definitely have certain types of continuity checks, which are outlined in your meter books. So stay tuned for that one. Connectors may be checked for continuity between the wire and the connector. Well, that is exactly what we're going to put to the test on our lab assignment today, right? So it's one thing to perform the connection, it's another thing to know that it is going to get the job done, right? That it's not going to overheat, it's not going to flash over, it's not going to cause any problems, right? So the connector may be tarnished, oxidized, or rusted. The connector may be loose. The wires may be incorrectly connected to plug connections, and switch contacts may be dirty or pitted. Such switches must be replaced rather than cleaned. So this is certainly valid, but as we look towards today's lab assignment, what other sources of error could occur as people are kind of performing their connectors? Why might some connections not be, let's just say, up to snuff, right? Well, by show of hands, who's first, who's not in the electrical field here, looking to get some hands-on experience? Cool, so you're in the right place. But again, informative and excuse says human error, right? Easy to do the right thing, hard to do the wrong thing. Well, if you've never done this before, well, we'll be extra cognizant of that. And the good news is you'll perform your first kind of wire termination here, and we're going to be able to electrically test it, because at the end of the day, that is going to be the ultimate kind of deciding factor of if you did a good job. Because I'm sure it'll look great. I'll look at it and be like, nice. But then it'll be up to you to electrically test that with the knowledge we've gained so far with our vector testing to be able to give it that 100%. Cool. So yeah, we've been at it for a while. Let's take a break until 8:30 while we gear up for the lab. All right, 8:30.